T-Test Explained in this app, and you can find the URL to the app right there, and you can also see the video explain the app here, the video we're watching right now. What I'm going to do is I'm going to talk about a statistical test called a T-Test, which tells you if the average of one group is different from the average of another. For example, if we were performing an experiment to find out whether a medication worked, if the average of the people who took the medication in terms of their symptoms was lower than the average of the people who hadn't. What we can do in this app is you can change the sample size, so the number of people in each group. You can change the mean of each group, the blue group and the green group, and also the standard deviation. So there you go, you can change the mean and the standard deviation. And so what a t-test does is it tells you if there is a difference between the averages. Now, before we get to do the t-test itself, we need to meet the assumptions of the test, because the test assumes a few things. And we can only really trust the t-test, or we need to be a bit cautious about the t-test. We need to be a bit cautious about the t-test if it doesn't meet some of these assumptions. So we need to check a few things in advance. And in this app, you can see it has a section here, t-test assumptions. One thing that the t-test assumes is that it assumes that each of the scores for each of the groups is normally distributed. So it assumes that the scores of the green group is normally distributed and the scores for the blue group is normally distributed. And we can test that with a statistical test called the Shapiro-Wilk test. Now, the Shapiro-Wilk, as with all tests of assumptions, we want it to be non-significant, which is to say p equal or above 0.05. And in this case, what you'll see is that yes, both of these are non-significant. P is equal to or above 0.05. The assumption of normality has been met for all the groups. This is good. And one thing you'll see with this app, by the way, is that that's always true, because the way the data has been simulated in the computer code, it's always going to be normal. Well, the other assumption you should know about is homogeneity of variance. Now, what that means is that each group needs to have a similar standard deviation. Homogeneity means similarity, variance is just standard deviation squared. So a t-test assumes that each group has a similar standard deviation, and we test that with a statistical test called Levene's test. Again, we want that to be non-significant, and in this case it is, because they both have similar standard deviations here, 7 and 8. Therefore, the homogeneity of variance, the assumption of homogeneity of variance is met, and both of these have been met. Therefore, all the assumptions of the t-test have been met. However, alternatively, if you change it like this to give them very different standard deviations, so what we can see here is the blue group now has a far lower standard deviation than the green group. Well, now that assumption of homogeneity of variance is not met. Look, this is a significant Levene's test. This assumption is not met, and it comes up with this warning sign: at least one assumption of the t-test has not been met. And that tells you, interpret the analysis with caution. We might not be able to trust its results. Now let's just go back to change those numbers back to what they were before, or at least so they're ready for the test. Yeah, let's have the numbers over here. So what we can see here is that when we're performing the t-test, we want to find out if the difference between the two means is big enough that we can be confident that there's a real difference in the population. We know there's a difference in the sample. We know that this mean is different to this mean, but we want to make sure that there's a difference in the population. So what student t is, it's a statistic given by the t-test. The t-test gives you a number called students t. Sometimes it's just called t, which is how many standard errors are the means away from each other. How many standard errors are they away from each other? And if you want to learn more about standard errors, I'd recommend you look at Megan Bernard's excellent toolkit on inferential statistics that you can find on Statistics Launchpad. And then from that student's t-statistic, then you can work out a p-value, and the p-value is the probability of seeing that difference in the samples. In the sample means if there was no difference in the population. So let's go through the results. So when you have a t-test, it's going to be written up, reported something like this. So t, and then before it actually gives the t-value, it gives you what's called the degrees of freedom. And degrees of freedom is basically how much information the test has, how many numbers the test has to perform its calculations. And the degrees of freedom normally is just sample size minus 1. But here we actually have two groups, and so it's the total sample size minus 2 because it's two groups. So we've got 50 people in each group, so that's a total sample size of 100, minus 1 from each group, that's degrees of freedom of 98. What you'll also see is that the sample size is going to change the results of the t-test because a larger sample means a smaller standard error. And then we get our t-statistic, and the t-statistic in this case is 4.16. And what that means is that these sample means are 4.16 standard errors away from each other. Now, sometimes the t-statistic might be a negative number because if what it does is the test is it subtracts one mean from the other, and if the second mean is larger, that subtraction will result in a negative number. But either way, it's just the difference between the means in terms of standard errors, how many standard errors they are apart from each other. And then it also gives you the p-value, and the p-value is the probability of seeing that difference, in the sample means if there was no difference in the population. Because what we do is we begin by assuming there's no difference in the population, we find the probability of that, and if that probability is low, less than 5, then we can take that idea and say, no, it's unlikely, throw it away. Throw away the idea that there's no difference. And we can say, because it's unlikely to see this difference if there is no difference in the population, we'll take that as a sign, statistically significant, a sign that there is a difference between the means. And so that's what the p of less than 0.05 means. Now, if you want to learn about that in a little bit more detail, what we can do in this app is we can also see what's going on behind the scenes in the t-test. So if you go up here for the distribution display, you can actually see the sampling distribution. Now, I'm not going to explain sampling distribution in a great deal of detail because this has been previously explained in the inferential statistics app, but the basic idea is that if we have lots and lots and lots and lots and lots and lots and lots of samples from the same population, what we can do is we can create a distribution of those sample means. So if we have a lot of different sample means from the same population, then there'll be a lot of sample means over here, not many sample means over here, not many sample means over here. What this display does here is it tells you how far the means are in terms of standard errors. So one mean is just shown as the middle, the real mean in the population, and then the other mean, the other black line, is shown over here. So what this does is this tells you how many standard errors the means are away from each other, because the axis is standard error. A standard error is just the standard deviation of the sampling distribution, and you can actually show the standard error here. And so what that means is that the standard error is the standard deviation of the sampling distribution, and what that means is that most of the time, so about 67% of the time, if you measure many means from a population, around 2/3 of the time the means would be between here and here. Okay, and so what we can see here is that that's the mean minus 1 standard error and plus 1 standard error, and we can also see, look at that t-statistic, it's 1, 2, 3. That's in fact over 4 standard errors apart. And so the t-statistic is how many standard errors the means are away from each other, because this gap here is the difference between the means. Now, what we can also do is we can look at the confidence interval that you would have learned about from the confidence interval discussion in inferential statistics in that toolkit, that 95% of our sample means, if they come from the same population, will be within this range here. And that means that if the difference between means is large enough that the other mean is in the critical region in the red here or further, that means that there's a less than 5% chance of seeing that difference between means if there's no difference between means in the population. So let's make that difference quite a bit smaller. So what we'll see here is if the difference between means is this small, well then they're both toward the middle of the sampling distribution. Well, it's entirely possible that they come from the same population and have the same mean. But if there's a big difference, look at a big difference like that, or even a larger one like this, the difference is so big that it's very unlikely that they come from the same population. And the reason I'm showing you this is because we're using the standard errors and the confidence interval in order to work out the p-value, the probability of seeing the probability that that there's no difference in the population, and that's where we get statistical significance. And so what we've done is we started with means, then standard deviations, worked our way up to standard errors, and now we've performed this statistical test. And what I'd like you to do now is I'd like you to change the mean and the standard deviation to see how this affects the results, as well as changing the sample size. And what I'd also like you to do is I'd like you to go to this display here where it's showing the sampling distribution and find out at which t-statistic does the difference become significant. And so that's t-tests explained.